In the previous example, we coined a term, log likelihood, and so we define the log likelihood learning to be the same as maximum likelihood learning, except that we take the log of probability data given hypothesis in order to simplify the computation of the maxima of probability d given h. So this logarithmic action on the probability is applied to simplify the computation that makes maximum likelihood learning the log likelihood learning in practice. Let us reimagine the same candy experiment by adding another component to the data point, which is the candy wrapper. So now our data point has two attributes. One of them, the candy flavor, which was cherry and lime as previously described, but the new one is the wrapper, which can be either green or red. And our job is to learn the hypothesis once again, but this time the hypothesis is slightly more complex because we now need to base our hypothesis not just on the candy flavor but also on the wrapper of the candy. The important thing to note is that there might be some correlation between the flavor and the wrapper. For example, the candy flavored, the cherry flavored candies are maybe more likely to be wrapped in the red wrapper or otherwise in green wrapper. That correlation is captured by a very simple Bayesian network here. So we are saying that whosoever filled the candy bag in the first place decided the wrapper of the candy based upon the flavor. So the flavor is the independent variable and the wrapper is considered as the dependent random variable. And so we are given two probabilities here. The probability that the wrapper we have a red wrapper for the cherry candy is θ1, and the probability that we have a red wrapper for the lime candy is θ2. So already we have these two parameters in the system that we wish to learn, and the third parameter is the same as before, the probability that the candy has a cherry flavor, that's theta. In this case, we need to apply the techniques of the Bayesian networks that we have learned before. So we wish to compute the posterior probabilities. We wish to compute the probability of data given hypothesis. So remember, the hypothesis has been parameterized by three variables, theta, θ1, and θ2. And the data has two components, the wrapper and the flavor. So the wrapper W and the flavor F, H theta, θ1, θ2. So here we apply the simplification of the Bayesian network, and so we say that this expression is equal to probability of wrapper given flavor and the hypothesis, and multiplied by the probability of flavor given the hypothesis. So as a result of this simplification, let's now take up an example. Supposing that we sample n candies from the bag, and out of those L candies we have L lime candies and C cherry candies, so that C plus L equals to n. Of the C cherry candies, we have RC many candies in the red wrappers and GC many candies in the green wrapper. And of the L lime candies that we have sampled from the bag, as many as R L number of candies had red wrapper, and as many as GL number of lime candies had the green wrappers, so that RC plus GC is equal to C and RL plus GL equals to L. I apologize for making this slide a bit more cluttered, but hopefully if you can zoom in, you can see how the expressions are written and how the calculations have been performed. Then, following the steps that are also given in the textbook, it can be shown that the probability of data given the hypothesis is given by the expression containing 6 product terms: theta c to the power c 1 minus theta to the power L, theta 1 to the power RC times 1 minus theta 1 to the power GC, theta 2 to the power RL times 1 minus theta 2 to the power GL. So once again, we wish to compute the maxima of this probability. So we compute the maxima by taking the logarithm, which simplifies the computation. And because P is a function of 3 parameters, in this case, theta, theta 1 and theta 2, so by using the first derivative technique for the computation of maxima, we take the partial derivative of L with respect to each one of these parameters. So partial L over partial theta 1 gives you, and then setting that partial derivative to 0 gives us the value of theta 1. If we take a partial derivative of L with reference to theta 2 and then setting that partial derivative to 0, we compute the value of theta 2, and taking a partial derivative of L with reference to theta, setting that derivative to 0 gives us the value of theta. So this is a generic framework of calculating the parameters using maximum likelihood or log likelihood learning. This example and its working has been detailed in the textbook as well. So you can work out the remaining details by yourself by referring to the textbook example. All the random variables that we have been working with so far have discrete nature. So in the candy example, the wrapper of the candy and the flavor of the candy could only acquire discrete values. So we've been working with discrete models so far, and we've seen the applicability of the maximum likelihood learning or the log likelihood learning for the discrete model. However, it should be noted that the maximum likelihood or the log likelihood learning can also work for continuous models. That is a model in which the random variables have continuous nature, in which case we don't actually deal directly with the probabilities, we deal with the probability density function. So one of the most famous probability density function that we are going to utilize in the remaining lecture is the Gaussian probability density function, which has 2 parameters, the mean and the variance. Also note that in case of Bayesian parameter learning, dropping the prior probability from the Bayesian learning may simplify the learning, as we did in case of the maximum likelihood learning. It may be less accurate in principle because we are really not taking into account the initial prior probability, and we are really trusting our data. Alternatively, one can also bring prior probability roll back and find other ways to simplify the computation. So we can reintroduce this term that we dropped for the maximum likelihood learning for the sake of simplicity. We can bring it back and find other ways to simplify the calculation of the posterior probabilities, as long as the expression of the posterior probability, which involves the product terms, is easy to compute. Let's look at how we can accomplish this in practice. If the prior probability PHI has a certain form such that it is represented by a carefully chosen probability density function which is parametric, then the computation of the posterior probability becomes more efficient and simple. In particular, the beta probability density function becomes useful in this case. So beta probability distribution has two parameters, A and B, and those parameters are used to give different shapes of beta distribution. So beta distribution is a parametric distribution, and changing the values of these parameters gives you different probability density functions. So for more details, you can refer to the relevant textbook chapter. How can we define and what are the benefits of the beta distribution? Here we are skipping the description of beta density function, but we are trying to understand how does it simplify the computation of the posterior probability. So assuming that prior has a beta probability density function of this form, then it is given by a constant times theta to the power a minus 1 and 1 minus theta to the power b minus 1. So remember, this is the beta density function of theta, and a and b are just the parameters of the density function. These are not the input. So the input to the function is theta. So this is the expression. Here this constant c is the normalization constant, and it depends on the value of a and b. So if you assume that the prior has a beta probability density function, then it turns out that the posterior also has a beta probability density function, and the update to the posterior becomes particularly simple. So here, probability data given hypothesis hi, and one of the things to note over here is that hi equals to theta. So theta is the random variable, and we know that the function of the random variable is the probability density function. So the expression of posterior is also a beta density function. However, the parameters have been updated. So right now this is a plus 1 comma b. So in each iteration of the Bayesian, or in this case the maximum yes, it is actually Bayesian. So in each iteration of the Bayesian learning, all we need to do is to update the parameters of the same density function, and that makes computation particularly easy and efficient. So that is the whole message behind choosing the prior probability density function to have a special shape. And in this case, we don't have to drop the prior for simplification. Rather, we can keep the prior, and we can still have an efficient computation of the posterior probabilities, thanks to the beta density function in this case. Note that learning can also be accomplished without computing the parameters of any probability density function or any probability expression. So that kind of learning is known as non-parametric learning. So to understand non-parametric learning, we first introduced the example of non-parametric learning, and the most famous example that comes to our mind is the k nearest neighbor learning. In particular, I will first introduce the supervised learning using k nearest neighbor method. Alright, so we're given a set of labeled data points. We are assuming that the data points have two components, x1 and x2. And we wish to classify an unseen data point, xq, to have either label 0 or label 1. And the criteria of this classification is very interesting. We say that if the majority of the neighboring k data points, that is the data points which are in the neighborhood of xq, let's take k of those data points, and if the majority of those k data points, assuming that k is an odd number, if the majority has label 0, then xq will also be classified with label 0. And if the majority of those data points have label 1, so will xq have label 1. So a common notation that is used to denote the set of neighbors or neighboring data points is NN, k, xq. So that specifies the data points in the neighborhood of xq, the unseen data points. Obviously, the criterion of the neighborhood comes from the idea of some distance measures. So we've been saying that the data points which are closest to the unseen data, xq. Now, just a quick reminder, we are saying that we know exactly what are the labels of the data set, that data points in the data set that we already have. So we know the labels of all the data points that we have been using for training. So those labels are shown here. Essentially, we have two kinds of label, the cross and the circles. The unseen data points are shown by different labels. In this example, the square and the steric. And so our job is to find out the label of these unseen data points. So we are saying that we have as many as 3 neighbors, that based upon whose labels we're going to decide the label of unseen data point. The other thing that we need in the nearest neighbor method is the closeness, to be able to quantify the closeness using some kind of a distance measure. So Minkowski distance is commonly used. The expression is given over here, and the expression of a distance has a parameter p, which is related to the norm of the vector. Essentially, if p equals to 1, this distance metric is same as the Manhattan distance that we discussed earlier. And if p is equal to 2, then it becomes Euclidean distance. So in this example, let's take p equals to 2, the Euclidean distance. Then if we look at the neighborhood of the black data point, then in this neighborhood we have 2 label 0 data point and 1 label 1 data point. So quite naturally we are going to assign label 0 to the square. And for the star, this is the opposite. We have more label 1 data points in the neighborhood than the label 0 data points. So we are going to assign label 1 to the steric. And this is how the k nearest neighbor method works in case of supervised learning. One of the reasons we brought up the k nearest neighbor method in the context of non-parametric learning was to introduce some methods to estimate the probability density function without referring to any parameters. So if we have a probability density function which we don't wish to specify with the help of parameters, that becomes a non-parametric estimation. Such a probability density function is non-analytical by nature. So we don't have any closed form expression. The only thing we can do is that we can represent that probability density function with the help of a graph. So visualization will be the key. So in those cases, we are going to show you a method of non-parametric estimation of probability density function using k nearest neighbor based method that we just described. So in this problem, we are given two component data points, once again x1 and x2, and we assume that all these data points came from some probability density function that we don't know of. So the labels are not given. They're, in this case, all the data points have the same label. The problem is different. We wish to compute the probability density functions which was used to generate these data points. And like we said earlier, that to achieve this goal, we don't wish to specify parameters, meaning that the underlying or the hidden probability density function does not have any analytical form. Therefore, it is non-parametric in nature, quite unlike the beta distribution, for example. Then if we use the k nearest neighbor learning principles, here is what we can do. We are going to select a set of location points where the density function needs to be estimated. So we are going to define some location points where we wish to estimate the density function. So in this example, we have taken three location points, one here, here, and here. Then we choose a value of k. So let's choose a value of k to be 5. And we are going to draw circles around each location point to encircle exactly k nearest data points. So in this case, we are going to draw the circle. So if we are here at this location where the density needs to be estimated, then we have to draw a very large circle so that we can have exactly five data points in that circle. On contrary, this location point circle will be much smaller. Here the data points are distributed in a way that they're very close to each other. So the circle is very small, and if we talk about the location here, then the circle is neither too small nor too large, and we can call this as a circle, a location of medium density. So why we are calling this as the medium density location? So the density is computed as follows. It equals k, which is fixed. In this case, k is 5. So k divided by the area of the circle gives you the density. So larger the circumference or the area of the circle, lower is the density. So lowest density in this region, whatever location point that you have in this region, is going to have a very low density here or here. If we select location point for the density estimation here, then we are going to get very high density. And over here, the density is neither too large nor too small. Then it is like a medium density region. So this low density here, high density here, and medium density here. And once we have obtained densities for large enough locations, then we would like to normalize all these densities to obtain a valid probability density function. How will the estimated density function actually look like if we try to visualize? Let's take an example from the textbook chapter 20. So the data points have again two components, x1 and x2, and the way they are distributed is shown here in this graph. And so you can easily identify regions of high density, such as here we'd have very few data points in this region, so a region of low density to be precise. And if you select locations for the density estimation somewhere around here, then the density will be large or high. Then they show that if we plot the density as the third axis being added to this graph, the other two axes are the same, x1 and x2, then you see the peaks. There are quite a lot of peaks, and this is the density estimation by encircling 3 nearest neighbor data points. So in the previous example, we fixed k to be 5. Here they are varying the k, so for 3 different values of k. So for k equals to 3, this is the estimate of the probability density function, and as you increase k, then the density function becomes smoother, so that for k equals to 40 it looks very smooth. But the overall nature of the density function can be visualized quite clearly here, that for large values of x1 and large values of x2, the density is high, and for low values of x1 x2 the density is small, and there might be some region where x1 and x2 are not too large, not too small. We have medium densities here. So this is an example. You can learn more about that from the textbook. In the beginning, we said that Bayesian approach to learning is particularly useful when we have missing data or missing information regarding the data. Now suppose in the k nearest neighbor learning problem, some data points have labels and others don't. So it's a case where we have some data points in the data set which came with some labels, such as 0 and 1 or cross and circle, but we have other data points represented by squares. They were not accompanied by the 0, 1 label. Still, if we wish to classify an unseen data point xq using the k nearest neighbor approach or a similar approach, then our best bet would be to try to guess the labels of the unlabeled data points. And for that we may resort to clustering. So this word clustering is particularly useful in the context of unsupervised learning, and we are going to talk more about that shortly. So in this example, we wish to assign labels. So our first task is to assign labels to the unknown or unlabeled data points, the squares. And once the clustering is performed, and if we could distribute these data points among different clusters, then all the data points in the same cluster will have the same labels. So if we construct 2 clusters, assuming that we can only have data points which can have label 0 or label 1, then we wish to go by 2 clusters. And once we have formed those clusters, assuming that those clusters are correct, then all the data points in any cluster will have the same label. A possible construction of 2 clusters are shown here. So you see we have 2 clusters, the red cluster assigning 0 label to the data points containing inside the cluster, and the blue cluster assigning label 1 to the data points contained therein. So as a first step, we're going to label these unknown labeled data points as squares inside the red clusters, and we're going to replace them with the crosses. So replace all these boxes inside the red cluster with crosses, and we're going to replace the squares inside the cluster 1 with the circles, and as a result we are going to get clustering that is shown here. So two clusters, cluster 0 and cluster 1, have subsumed the unlabeled data points therein, and here we are making an assumption that the clusters do not overlap. Although we should remember that this is not an essential assumption for the type of learning that we are going to discuss in the context of unsupervised clustering. But in this case, it is an assumption that we'll go by. Then the question is, how can we ensure that the clustering is correct? So the question is, how can we validate our clusters? For that, we calculate the centroid of each cluster, C0 and C1, the center point or the centroid, and we are going to judge the authenticity of the cluster if all the data points inside the clusters, they are closer to the centroid of that cluster than they are to the centroid of the other cluster. So if all the circle data points are closer to the centroid C1 than they are to the centroid C0 of the other cluster, and if this condition is satisfied for both the clusters, then the clustering is fine. Take an example of the centroids that I have indicated here, C0 and C1. By the way, as a note of caution, these centroids have been chosen somewhat arbitrarily, and they are not chosen according to the exact method for the centroid calculation. But suppose this is the centroid of the cluster 0. The C0 is the centroid of cluster 0, and C1 is the centroid of the cluster 1. Then if the clustering is correct, then all the crosses should be closer to centroid C0 than they are to the centroid C1. So any cross should be closer to C0 than it is to C1. And obviously in this case we can see that this is not entirely correct. For instance, this data point which has label 1 seems to be closer to C0 than it is to C1. So obviously there is some issue in the clustering. So this brings up another question: how can we fix the clusters? And the process of correcting our cluster can involve either relocating these centroids if possible, or we are going to redefine the clusters. And sometimes redefining the cluster can be a lot easier, as we shall see in this case. So if we redefine our clusters, then these two data points which were initially unlabeled, they could go to either clusters, have now been subsumed in the red cluster or cluster 0. So cluster 0 has been modified and it now contains more data points, and the cluster 1 has now lost 2 data points, and the centroid location has also been shown here. So with the inclusion of the new data points, we have 2 new or 2 different or updated clusters, and we calculate the centroid C1 and C2 for the new clusters, and if the 2 conditions about the closeness of data points of any cluster to the centroid has been satisfied, then we can be assured that our clustering is correct. In some sense, as you can already see, that the process of fixing or correcting the cluster may take several iterations, may take several attempts, and the clustering process will eventually stop once these 2 conditions have been satisfied. So in this example, after a couple of hit and trial methods, we have finally come up with a reasonable clustering which satisfies both these conditions. So the algorithm will stop here, and once we have these clusters, then we have essentially provided labels to the initially unlabeled data points that were given as part of the problem. And also, once the clusters have been formed, then we can easily classify an unseen data points depending upon where does it fall. So if the unseen data point falls here, then it is also going to be labeled 0. Whereas if the unseen data point falls in the blue cluster over here, unseen data point comes over here, then it is going to get labeled 1. So this is all summarized on this slide. Assign label cross or 0 to the unseen data point xq depending upon its closeness to the centroid C0 or C1. And this method of clustering is known as the k-means clustering. It is a form of unsupervised clustering or unsupervised learning, and it is closely associated with the Voronoi diagram construction that is used in finding the shortest path for the robot navigation problem in the field of robotics. Finally, we are going to conclude our discussion with the description of another famous form of unsupervised learning, that is learning Gaussian mixture models. In this problem, we wish to distribute unlabeled n data points among k Gaussian clusters such that probability Pij is maximized. And what is this probability Pij that we need to discuss here? So probability Pij is the probability that the jth data point belongs to the ith Gaussian cluster. So that's what probability Pij represents. So we're going to further explore this probability expression both mathematically and visually. So mathematically, this probability is proportional to the probability density function specified by the Gaussian random variable. So the expression is the same as you can see. This is the probability density function expression of the Gaussian or normal random variable, and it is representing the bell-shaped curve that all of us are quite familiar with. Notice that this probability has been, we've been saying that this probability is proportional to this expression because probability value has a restriction that it needs to be less than 1 and less than or equal to 1 and greater than or equal to 0, whereas the probability density function can have value which may not respect these limits. So we have to be careful. That's why I have used this constant alpha here. Anyway, so this probability Pij will have a higher value if the data point xj is closer to the mean. So here you can see that the maximum value of this probability is achieved when xj approaches the mean value of the Gaussian random variable. So mean of the ith Gaussian random variable, which we are now associating with the Gaussian cluster, that is mu I, and the corresponding standard deviation is sigma I. And so if we wish to maximize the value of Pij, then we wish to reduce the difference between the mean value of the cluster and the difference between the mean value of the cluster and the value of the data point. And the value of the data point, as we know, is given as part of the problem, the training problem. That is fixed. We cannot do anything about it. What we can do to maximize this probability is that we can adjust the mean and the standard deviation of the Gaussian random variable, which is actually a clustering, which is used to cluster data points in this case. So therefore, we are calling it as the Gaussian cluster. So the word Gaussian cluster will make more sense in the next few slides. So just hold your horses for the moment. So one of the things that we have learned over here is that we would like to move the Gaussian cluster so that its mean is as close to the data point value xj as possible, and the standard deviation sigma I is close to 0, and that is when Pij has a maximum value. So we understood why xj needed to be closer to the mean value, but it is also important to understand why reducing the standard deviation is important. That's because in the previous slide, if you increase sigma I, then Pij reduces, or increasing sigma I lowers Pij and vice versa. So we wish to minimize the variance or the standard deviation, and we wish to minimize the difference between the mean and the data point value. And this is how we try to fit a cluster to one single data point by minimizing the difference between data point and the mean of the cluster and reducing the variance. But we are not working with single data points. Instead, we have a large number of data points, x1 through xd to be specific. And as part of the homework exercise, you're going to show that one can fit a cluster to multiple data points using the log likelihood maximization technique that we discussed earlier. One can show that the best fit is obtained when the mean of the cluster equals the statistical mean value of the data points. Likewise, the standard deviation of the Gaussian cluster equals the statistical standard deviation of the data points. If those conditions are satisfied, then we are going to have the best fit for the cluster, in this case cluster I. So this is an example for visualizing how a best fit can take place. So we have an example of single component data points. So this is the data point axis. So we're assuming that we have single valued data points. The data points have only one component. So this is along this axis. And the Gaussian cluster that we have fitted to these data points, shown by the crosses here. So you see these crosses here. There are a lot of data points in this region. So the cluster is centered here. The highest value, the mean value, is centered where we have a large number of data points. As we move outward to the left or towards the right, then the density of data points also reduces, and so will be the values of the probabilities. So that this is how the cluster fitting makes intuitive sense using the visualization that we have just discussed. We are going to specifically look at the case of fitting two clusters C1 and C2 to the given set of data points. So the two clusters have different means and quite visibly different standard deviation values. So cluster C2 has lower standard deviation, therefore it has higher probability value at its mean, and the red cluster, the cluster C1, is more spread out and it has a lower peak value, that is the value at the mean mu1. Then once we have overlaid these clusters, then we wish to distribute all the data points to either we wish to split data points among cluster C1 and C2. And the criteria is that for any given data point X, if the cluster 1 has higher probability value for that data point compared to cluster 2, then we are going to assign, we are going to ascribe that data point to cluster C1. So it will going to have a label, say 1, or label specified by cluster C1. So let's take an example of a data point here. So this data point has a higher probability value in cluster C1. So we are going to label this with red color. So that's red here. And if we look at the data point over here, then this data point, for this data point, cluster C2 has higher value than C1. So we are going to color this data point with blue color here. And so we do this for all the data points, and now we have two different colored data points, the blue colored data points and the red color data points. So the important thing to note is the criterion. We are going to distribute data points to the clusters based upon the corresponding probability values, and that's the most important thing that we need to understand. So once we have completed the distribution, we can actually make a cluster. So we can make a red cluster shown here. So the red cluster is actually, it has two parts. So red cluster has two parts. So it is encapsulating points, some of these points on the extreme right and the remaining on the left hand side. The blue cluster on the other hand is a bit smaller compared to the red cluster. It has few data points. So once this allocation has been done, then we are going to refit these clusters by recalculating the values of their mean and the standard deviation for both the clusters. So this is a refitting step in which we recalculate the mean and the standard deviation for both the clusters. And this recalculation will be based upon the respective statistical mean and the standard deviation of the data points for a given cluster. So if we say that these blue cluster data points, they belong to blue clusters, then the mean of the cluster should be consistent with the statistical mean of these data points. Similarly, if we say that all these red cluster data points belong to cluster C1, then the mean of the red cluster should be consistent or should be equal to the statistical mean of these red data points, the red label data points that we have just assigned. So if we do that, then we notice that the cluster mean and the standard deviation have now changed. These are shown here. So a consequence of refitting is that the cluster will change based upon the labels that we have just updated. So the updated labels require us to refit the clusters. Once the clusters have been refitted, then we are going to reassign data points to the clusters as before, based upon the same criterion. So in a sense, this is a two-step process: reassign the data points, refit the clusters, then reassign and then refit. So in this case, when we reassign the data points, then we have a blue cluster here and a red cluster. And this in this update, you can see that the fitting seems more appropriate. All the blue cluster data points, they are well fitted to the blue clusters, and all the red cluster data points, they seem to be quite fitted to the red clusters. And if you perform a couple more iterations, I am fairly confident that the cluster mean and the standard deviation values will not change significantly, and that's where the algorithm will begin to converge. Already here you can see that both clusters are fitting much better to the data points. So if we summarize this Gaussian mixed model learning problem, it is actually based upon two steps that work in tandem. The recalculation or refitting step, in which we update the mean and the standard deviation values of the clusters based upon the updated distribution of the data points. So we are saying that update the labels of the data points, and then based upon that update, recalculate the values of the mean and the standard deviation. So after this refitting and recalculating the parameter values, we are going to redistribute the data points to the new clusters. And as a result of this redistribution, we are going to examine if our current fit is adequate. If not, then we go back to recalculate and refit, and then based upon this new fitting, we are going to reallocate the data points. And this will this algorithm actually goes back and forth between these two steps, and we shall keep on repeating these steps until the cluster mean and standard deviation values converge. And that is where we stop the algorithm, and we expect to obtain some good, if not the best, clustering of the data points. This algorithm is known as the expectation maximization algorithm. It is a two-step algorithm, the E step and the M step. The E step is known as the expectation update step, and it maps to the recalculation of the cluster parameters. The M step is actually the redistribution of data points among the clusters. By working in tandem, the E and the M step make sure that the algorithm converges to some maxima. It doesn't guarantee the convergence to the global maxima, but it does guarantee convergence to some maxima that gives us the appropriate clustering of the data points. So the maxima of the probability values, Pij, that we described in the beginning. In case of two-dimensional data points, this is an example in the textbook. We work with the bivariant Gaussian mixture model. So if you happen to know about the bivariant Gaussian random variable, it is a two-dimensional Gaussian random variable. So we work with two means and two standard deviation as well as a covariance or correlation parameters to specify one cluster. So essentially we have as many as 5 parameters describing one cluster rather than 2. So it is slightly more complex. That's why I did not include that in the main discussion. But just so that you know, this is figure 20.11, and so we're given our two-dimensional data points and we wish to fit 3 Gaussian clusters to these data points, and these are shown over here. An important thing to note is that 2 of these clusters look perfectly circular, but one of them has a more elliptical nature, and that remains part of your homework problem to explore under what circumstances do we have an elliptical cluster, or a cluster which exhibits the shape of an ellipse. So what are those circumstances? What are those properties in the data which gives you an elliptical clusters? An extensive textbook reading is required for this lengthy lecture. We have chapter 20 topics, 20.1, 20.2.1, 20.2.3 and 20.2.4, and then 20.2.6 and 20.3.1. So all of these topics are very important for the in-depth understanding of the topics that we have discussed in our lecture today, and I would strongly recommend students to look at any relevant material which can help you obtain better understanding of these concepts. The topics that we have covered today are quite dense by nature, so extensive textbook reading is therefore highly recommended. Your homework exercise has 2 components. In the first part, you're going to show that the maximum likelihood, log likelihood of data given Gaussian density function, which is treated as hypothesis, occurs when the mean of the Gaussian density function equals the statistical mean of the data, and the variance of the Gaussian density function equals the statistical variance of the data. And if you can remember, we used this result in our discussion on Gaussian mixture model learning problem. And you're also required to briefly explain under what circumstances do we get elliptical clusters in bivariate Gaussian mixture learning problem. Alright, so with that, I would like to formally conclude my discussion today. I hope to see you in our Q&A session scheduled on Thursday afternoon at 3 p.m. Till then, take care and goodbye.